Hey! Welcome to an exclusive Mr. Adams video lecture. Where today we're talking about ballistics. Part 1. Ballistics is the trajectory in the study of trajectory of objects that have been shot out of something. And the way that usually starts off is we have to learn about what happens when an object is just at the whim of the Earth. In gravity on Earth, we have to see what objects are when they fall. How can we describe objects when they are falling? We have to learn some rules. First of all, if we go down to our vocabulary pool, what we need to understand, we need to know these different things. And first, we just need to understand projectile is the object that is going to be shot. Trajectory is the path that this object takes. And then the peak is when it gets to its highest point in its trajectory. I have a couple different simulations to help you understand some of the properties of ballistics or objects that are going in the air. If I were to put these objects into a vacuum, I have these different masses that have half a kilogram, and then I have some lighter things. And this is like a feather. And we all know that on Earth, feathers drop at a pretty slow rate. However, if we have a vacuum, all of these objects are going to fall at the exact same rate. And when you have a vacuum on, then that means that you are taking away the air resistance. Now, air resistance is a function of an object's velocity and its surface area, but it is a differential equation. We don't have the mathematical tools to deal with that until we're juniors in college. We reset it. So this to say that if we were not in a vacuum and the objects were falling, we could see that they would be at different rates. But in this class, we are going to assume that we are in a perfect little vacuum, besides a few little different scenarios. So what is the rate, you might be asking, at which the objects fall? Well, on Earth, it's a particular number. The reason why I know it's a particular number is because if I take this lacrosse ball and this significantly lighter rubber duck, and I showed you all this in class, actually, period 4, I forgot to show you, sorry. If I take the two of these and I drop them, they land at the exact same time. Now, the ball bounced up because it's much more elastic. But all objects, even if they have different masses, they fall at the same rate. Taking a look at Earth. If we were to drop an object 1 kilometer away from the surface of these different planets / stars, the sun, it would take 2.7 seconds. That's terrifying. The sun has a lot of mass. It's going to cause objects to fall greatly. Its gravity is so great that it has the entire solar system revolving around it. That's scary. We continue on. Next up, Jupiter. 25 meters per second squared. That's fast. Sun was 274 meters per second squared. That is absolutely terrifying. The Earth, a much more manageable 1G, or 9.8 meters per second squared. In this class, we will be referring to it as 10 meters per second squared. And that's just not me who's saying that. That's AP Physics 1, College Board, who is saying that. The gravity on Jupiter is about 2.5 times that of the Earth. So Jupiter's gravitational field is 2.5 Gs. That G is a form of a unit of acceleration that is used to talk about the ratio between the acceleration of an object compared to object that is accelerating on Earth. So if you have an object that is accelerating with 2 Gs, that is going to be 19.6 meters per second squared, or in this class, 20 meters per second squared. Now, all objects fall at the same rate, no matter what the mass. Just one more thing to show this. If we take this little cannon simulation, we have an object, shoot it up in the air. It's a little pumpkin. Pumpkins are heavy, not that heavy. If I take the time that it took to get back to the ground, 3.06 seconds. I'm going to change this. Pumpkins are different than pianos. We shoot a piano into the air. 3.06 seconds. Would you look at that? It's the same. Moving on. The velocity is the same at the same heights on the way up and down. What does that mean? I'm going to show you. This is actually a boo-boo simulation. I'm going to this one. No, I'm going to... I lost it. There we go. I found it. So I'm going to change the angle of this to 0 degrees or 90 degrees. So that's shooting straight up in the air. This object. This simulation tells me what the object is. Right when it starts off, it's going to go with 25 meters per second. Goes up into the air. Comes back down. Whoop-de-doo. What I'm going to do is I'm going to reset that, and we're going to take a look at the velocity when it gets to 10. Oh, that was way too fast. Oh, goodness. I'm trash. I'm going to take it at the 20. Aha. I'm going to go back down exactly to where it hits 20. This is about 20. 15.3 meters per second. Going upward. I'm going to let it go, and it's going to come back down to the 20. It's a little beyond that. Yeah, there we go. 15.3. Negative 15.3 meters per second. It's the same on the way up as it is on the way down. And you notice that this is negative. So what's between positive and negative? If I go up to the top and we're going positive, and then it switches to going to negative on the way down, then what we have to do is that to get between positive and negative, the point at which it reaches the top, the velocity for a very small period of time is going to be 0 meters per second. The velocity at the peak of the projectile is 0 meters per second when it's in the y direction. Now, the time that it takes to come back down is going to be the same amount of time it took to get to the peak. The time that it took to get to the peak is the same as it was to get away from the peak. So this 2.55 seconds, if I let it resume, go back down to where it was launched from the 0. If I go back down to the 0, 5.1, which is 2.55 times 2, we did it. We did it, everybody. Okay, that's what you need to know for falling objects. That's what you need to know about our first introduction to ballistics. I hope it wasn't too painful mentally. See you tomorrow.